Hey everyone, welcome to The Explainer. I am so excited to have you here today because we are going to unpack something truly mind-blowing. We're talking about the invisible force that literally powers our entire modern world. From the device you're using right this second to the massive machines building our cities, it all comes down to the precise manipulation of electromagnetism and steady currents. So, if you've ever wondered how just flipping a simple switch can do so much heavy lifting, you are in exactly the right place. Here's our game plan for today. We're going to start with the spark of electromagnetism, look at how to shape the magnetic field, engineer an electromagnet, spot them in our daily lives, crunch the numbers, and cap it off with a quick final quiz. All right, part 1, the spark of electromagnetism. Let's look at where this all began. So, electromagnetism. Simply put, it's the phenomenon where an electric current produces a magnetic field. It sounds straightforward now, but the way we discovered this, it was a total accident. A physicist named Hans Christian Ørsted was actually in the middle of a completely different experiment when he noticed something weird. Every time he switched on a nearby electric circuit, a compass needle on his desk kept twitching. That accidental little twitch, that proved that electricity generates a magnetic field. Literally a world-changing realization that gave birth to modern tech. Now, before we really throw electricity into the mix, let's quickly recap what we know about regular permanent magnets. You know the drill, right? They've got fixed north and south poles. The invisible magnetic field lines around them tell us exactly which way the force is pushing or pulling. And the golden rule of magnetism, like poles repel, opposite poles attract. But here's the thing, you can't turn a permanent magnet off. Its power is totally fixed by whatever material it's made of. Just keep that limitation in mind because electricity is about to completely shatter it. Moving right along to part 2, shaping the magnetic field and how we actually control it. Okay, I need you to actually do something with me right now. Seriously, wherever you are, unless you're driving, hold up your right hand. Just give me a thumbs up. This little gesture is actually the physical key to understanding the invisible geometry of electromagnetism. You are looking at the famous right-hand thumb rule. It's like a built-in physics cheat code on your wrist. Here's how it works. Imagine you're gripping a wire that's carrying electricity. If you point your thumb in the direction the current is flowing, the natural way your fingers curl around that wire, that shows you the exact direction of the magnetic field lines. Current goes up, your fingers curl counterclockwise. If the current flows down, point your thumb down, and boom, your fingers naturally reverse and curl clockwise. And seeing this rule in action is so cool because it shows how we can totally manipulate these fields. If you take that straight wire and bend it into a circular loop, those field lines start bunching up in the center, combining their force. Now, take it one step farther. Wrap that wire round and round into a tight coil, what engineers call a solenoid. Suddenly, you've aligned all those separate magnetic loops into one unified, incredibly intense magnetic field shooting right down the center of the coil. You've basically just built a magnetic cannon. All right, let's dive into part 3, engineering the electromagnet. This is where we build some real power. Building an electromagnet is shockingly simple. It's really just a 3-step recipe. Step 1, you grab a soft iron core. Honestly, even a simple iron nail works. Step 2, wrap it tightly in an insulated copper wire coil to create that solenoid shape we just talked about. And step 3, connect the ends of that coil to a steady power source, like a battery. The second you close that circuit, the iron core hugely amplifies the coil's magnetic field. Boom, you've got an electromagnet. But you know, engineers don't just want a magnet. They want a magnet they can completely boss around. And by tweaking just 3 variables, you can crank the power up or down on demand. You can increase the number of wire turns wrapped around the core. You can pump up the amount of electric current flowing through the wire. Or you make sure you're using a really good soft iron core to concentrate the field. Mess with any of these and your magnetic strength changes instantly. Now look at this direct comparison. This table is exactly why electromagnets are the absolute heavyweights of modern tech. A permanent magnet, its strength is fixed by its material. You have zero control over it and the poles never change. But an electromagnet, the source is current. The strength is completely variable and can be massively stronger. The control is absolute. You just flip a switch to turn it off. And just by swapping the battery connections, you can instantly reverse the north and south poles. It's this total control that makes heavy industry and modern medicine even possible. Which brings us nicely to part 4, electromagnetism in daily life. The tech we rely on every single day. It is crazy to think about, but the exact same basic setup, A steady current flowing through a coiled wire does so many wildly different things. It can rapidly switch on and off to strike an electric doorbell. It vibrates against a regular magnet to blast music out of your loudspeakers. It scales up to those massive scrapyard cranes to effortlessly pick up crushed cars and then drop them the second the operator cuts the power. It drives our electric cars, and it creates the intense imaging fields inside hospital MRI machines that literally save lives. Same invisible force, just engineered differently. Okay, let's switch gears for part 5, by the numbers. Let's look at the math behind the magic. For all the focused learners, especially the grade 10 students and MCAT folks tuning into this explainer, let's nail down these mathematical relationships. The big question is, how exactly do current and distance change the strength of that magnetic field? Well, pushing more current through the wire obviously makes the field stronger, but what happens as you step away from it? It all comes down to an inverse relationship, which we represent as 1/d, where d is the distance. Basically, the strength of the magnetic field drops off very fast the further away you get from the wire. So if you double your distance from the conductor, the magnetic strength becomes just a fraction of what it was up close. It's a very precise mathematical drop-off, and engineers have to calculate this perfectly when they're designing everything from tiny microchips to massive power grids. And finally, part 6, the final quiz. Time to see what stuck. Question 1 for you. Which rule tells us the direction of the magnetic field around a straight current-carrying wire? Take a second and lock your answer in mentally. All right, time's up. It's the right-hand thumb rule. I really hope you just threw a thumbs up at your screen again. Remember, thumb points with the current, curled fingers show the magnetic field. Moving to question 2, testing your engineering recall. What is one direct, hands-on way to crank up the strength of an electromagnet? Think back to those 3 variables we just broke down.
Got it? You just need to increase the number of wire turns in your coil or bump up the steady current. And yeah, making sure you have that soft iron core is the third big one. Awesome job if you nailed those. You've just successfully navigated some pretty heavy physics concepts.
To wrap things up today, let's go right back to that beautiful, simple realization from Hans Christian Ørsted. An electric current produces a magnetic field. From one accidental twitching compass needle, human curiosity bridged the gap between 2 natural phenomena. We permanently united electricity and magnetism into a tool that we can bend, shape, and command with the flick of a switch. So here's the thought to take with you. If a simple, steady current running through a coil can do everything from ringing a doorbell to powering a life-saving MRI, what invisible forces will you harness next with everything you're learning? Thank you so much for joining me today. I absolutely love unpacking these topics with you. If this explainer helped you lock in these concepts, please like, share, and subscribe for more MCAT and high-level physics explainers. Keep learning, stay curious, and I'll catch you in the next one.